not a bad.
Well, not fair, but. Didn't get the connections yesterday.
Did you get it? Oh. It was like, can you make us? You can make us work. Oops, was one of them. There were so many. That was one of them. I think, yeah, I can pull up on the house. Like, there's no places that are like them.
Let's see, so I wanted to go through the homework from this, let's see, let me hide this thing. All right, so I'm kind of a little bit late today, but anyway, so yeah, so I went through this paper last time, right? Oh, can you guys, Willow, can you hear me? Say something if you can hear me. Or Jeremiah. What the audio is working on this thing?
I can hear you.
You can hear it? Was that in here? Oh, he said, all right, I said he was in here. All right, definitely losing my mind today. So anyway, most people kind of got the gist of what was going on in this paper. So it's like a surfactant. And they modified the surfactant to put 2 tertiary amines on it. And then they do a cationic anionic mix to get solubility for that, because it was kind of insoluble before. And they have some explanation of the cartoon about how that works. So the homework was basically go through a bunch of these molecules and just say what's hydrophobic, what's hydrophilic. So basically just to get you kind of familiar with that field. I don't know, that's a little bit helpful because you see these long names and you have no idea like what's going on. So if you kind of search for the and they're all going to have this chain that comes from some kind of animal fat or plant fat, you know, so it basically had glycerin holding the 3 fatty acids together, and it was broken apart, and you get just the carboxylic acid, which is soap, and then you saponify it with or you sulfonate it with sulfuric acid, and you get a sulfonate group, or you put an amine on it, I guess with ammonia, I think. But anyway, so that's kind of the scheme of all the surfactants mostly, except for the what's called non-ionic surfactants, which is usually it's a mixture of so you'll see in industry, you'll see a lot of non-ionic surfactants too, which are going to be like almost so polyethylene oxide or polyglycolic acid is like polyethylene, and then let's see, this guy is going to be happy there. So it's polyethylene, and then you put an ether on it. Right, so that's called PEG. It's called PEG or PEO, polyethylene oxide. That's water soluble, so it's got a UCSD, like if you do temperature composition, it phase separates when you cool it, which is like a normal, like salt and water comes out. And a lot of polymers, so that's called a UCST. This is the upper critical point. And then most polymers are going to have an LCSD. So when you heat it up, so if you try to clean up a gooey polymer with hot water, it won't clean up. When you try to use ice water, and it immediately dissolves. Right, so like this is pretty common in polymers. We'll talk about why that is, but anyway, so this has a UCSD in water, and basically it's water soluble, and its partner, which is polypropylene oxide, so PPO, is insoluble in water. Right, so you could say that this is more like an oil, and that's more like water, kind of. So it's got like a del minus here. Both have a del minus. This one's insoluble. So you make a block copolymer like PEO, PPO, that's called pluronic, and that's a non-ionic surfactant. So the PEO will go with water end, and PPO will go with the dirt end. And this is like hand gel, like the antiseptic, whatever, ethanol and this thing mixed together makes a gel. And then this is drug deliveries, biomedical, it uses a lot. Like the coating on stents has the stuff in it for heart stents and things. So basically this is like all over the place. It's like Triton X100 is a common one, and it's like PEO, PPO, and it's got like aromatic groups on the end of it. So you can have all kinds of complicated oleophilic end groups added to that motif. You can also have tri-block copolymers of that. So like PPO in the middle, right? So you can have like whatever you want. You can keep adding blocks to it. So maybe we'll talk about anionic polymerization. So anyway, that's another kind of surfactant, non-ionic. And then there's also a third kind is zwitterionic. So you have kind of like this, like if you could join, if you have both a anionic and a cationic head group, they're like coupled together. So you have a kind of a longer head group and it's got two ionic groups, plus and minus, right? So I think zwitter means like, I don't know what zwitter means. It's kind of a strange looking word. Anyway, so that's kind of, I went through that before. Anyway, so then it's like, so this thing, this is about sodium toluate. So these are called, yeah. Oh, sorry, yeah. All right. Sorry about that.
Okay, so you were talking about the ionic surfactants. In the homework, I noticed that there were some like within the surfactants, like covalent bondings within them too as well. What is like the main difference between like the ionic surfactants and like the covalent? Because there was some that would just have a covalent, I believe, and then
What do you mean covalent? Like
is there
that?
like main any
Like some of them have like
differences?
unsaturated chains. Is that what you mean? Like
I
the,
think so. I'm
so it's
kinda
like an
new to that.
alkane, like a zigzag, and there's a double bond in the middle of it.
Yeah.
Yeah. So I don't think anyone knows, so like some of them they think are better than others. And I mean, it adds the rigidity to the chains. It's all it comes down, the science of it kind of comes down to the geometry of how it fits in. A double bond is like a fixed planar structure, whereas a single bond, it can spin around. It's like, in other words, it's called conjugated, right? So if you have two double bonds, that all forms a plane. Like benzene is a planar molecule because all the double bonds are planar. So there it's double, single, right? That's a conjugated molecule. So basically you stick that kind of thing, it makes it a rigid end group on it, and that can change just the geometry of how they pack together. I mean, I think as far as I can see, like there's a theory behind the packing of these things. It comes down to just what the geometry of how those things are going to fit. And then that geometry changes when you have like, so if you add salt to it, the geometry changes because you get what they call screening. Okay, so we'll talk about that a little bit later, but basically, if you have like a plus charge here and say a plus charge here, there's some interaction between them. And if you add in other pluses, so then like that interaction disappears. So the higher the concentration goes with 1 over the square root of the concentration, there's something called the screening length, which would be like the distance that plus charge can feel that other plus charge. So it's kind of like if you have a person and they're screaming, like then you're over here, you're pretty far away, you can hear them, but if there's other people talking in between, you can't hear them. And the more people talking in between, the distance that you can hear goes with 1 over the square root of concentration.
So that kind of gets into like electric fields type ish.
Yeah, it's coulombic. It's like plus minus, they either repel or attract, coulombic interactions. Right. So basically, as you salt out, so as you put salt in, it's going to block the interactions between the pluses along the micelle, right? So, or if they're anionic, the minuses. So, and then so the more salt you add in, they become less ionic essentially. Like they don't act as much like ions repelling each other. And then that'll change the geometry of how the thing fits together. So somehow that affects so if you could draw a cartoon of like triangles fitting together and change the shape of the triangles, then the shape of the micelle will change, That's more or less the theme of what people do in this. For like, and basically that's even beyond what most industrial people like are working in the field know about it, Like they don't, so basically that's at some point that becomes like esoteric, you know, I'm not sure this is fully understood. Anyway, so so this is about this lauryl sulfate thing. So the toluol thing, right? So basically toluate. So this is like these hydrotropes is kind of a subject. So I didn't remember that when I wrote the quiz. Basically, those things are all called hydrotropes. They add in, and even mentions in here in wiki.
Let me even switch this.
Oh, sorry, this is a wiki page. I put a link up to it on the web page, but so even mentions like personal care to allow more concentrated, so basically concentrated washing detergent, like concentrated Tide in the little bottle instead of the big one, right? So that's basically like they show a few of these here. And then, oh, they also mentioned that ATP, which is like an energy thing in biology, acts like that for something, aggregation of proteins or something. So it also allows, because in your body, so the polymers in your body are at like super concentrated conditions, way beyond, like usually if you're doing solution work, like in industry, it's dilute, pretty dilute. So in order to pack so many proteins together and not have them precipitate out, then you need to have something like, apparently there's some kind of mimicry between, I think this was discovered in industry before they realized that the same thing was happening in biology. It's like reverse biomimicry, like biology has copied industry, you know, more or less. But anyway, so they mentioned that in here too. It's kind of interesting. Anyway, so there's a lot to it. Hopefully you can just kind of get a little feel for this stuff. Anyway, so this was, I was hoping that you would go in and like take the cartoon and then draw your own cartoon, but nobody did that. I should have said draw a cartoon. You know? So any of these things, the only way you're going to understand them is by cartoon pictures, really, right? I mean, there's a few things you can know about measuring the interaction distances between the head groups and how many counter ions are associated with it, but basically it's going to end up being a cartoon. So I hope that you guys would have done that. No one did, didn't matter, but basically a cartoon would have been good here. Just kind of showing how the little blocks could fit together. That's the idea, you know, somehow. So there isn't a definite right or wrong answer in that. I think that some of you went to the text of the paper and he mentioned some stuff about why he's adding this anionic polymer to it, anionic surfactant to it. Anyway, so that was okay, I guess. And then the ratios, blah, blah, blah. Let's see, this is figure 3 verifies. So this couple people got, so the question is really like, what's the signature of a polymer if you measure viscosity and shear rate? I should mention like, well, I should mention just the way this thing works. So you have most of the time in these kind of measurements, so there's two kinds of viscometers. There's like a cup and bob viscometer. It's called a couette viscometer. So you spin the bob, you put your fluid into the cup. There's a gap here. And you measure the torque on this and the speed, right? And the speed gives you the speed is like the velocity, say the velocity of a wall against a fixed wall. And then if it's laminar flow, you're going to assume a constant velocity gradient. Or Newtonian flow, you get a constant velocity gradient. So dV dy, and that's this shear rate, m dot, which is also the strain. So dx dy dt, right? So it's those. So you can have the change in velocity with position going through the gap, or you can have the change in position, that position, with that position versus rate of time, right? So it's kind of two ways to look at shear rate. Anyway, so for us, think of a deck of cards, right? When you push the top card, they all go evenly. So basically, deck of cards flow is called laminar flow versus turbulent flow, which would be like this kind of weird thing, right? So the assumption is that you stick to the wall at the bottom, you know? And then the force you put on it, and then the area that you apply the force to. So it's a force in X direction, it's an area in the Y direction, and the normal to the area is the Y. So that's the shear stress. Right, so you have shear stress, shear strain proportional to each other, this viscosity. That's the things being done. So another geometry is you have, and this is in Polymer Labs, you're going to see this either cone and plate rheometer or plate rheometer. Right? And the reason for this geometry, the problem with this thing is that if you go across that gap, the shear rate changes because you have different kind of distances to the wall if it's a cylindrical tube. So this isn't constant shear rate across the gap. In this geometry, because the gap y changes and the velocity changes, and they're both proportional to the radius. So that cancels out. So it's a constant shear rate across the gap on that one. That means you can, with this viscometer, you can do the plot of like this viscosity versus shear rate because it's constant shear rate. In this one, you just get kind of one number with a spin number. And it's not exactly perfect. But if you're doing something like paint, like Sherwin-Williams or something, or if you go to a paint store, they just stick a thing into the paint, into the bucket of paint and just spin it and get this. So it's kind of a modification of this thing, this couette. But there's a lot of different ways to get the viscosity. The paint bucket one is the simplest. You just have a rod just on a electric drill kind of thing, and you stick it into it and you get the viscosity. So this cone and plate is better. So that allows you to shift the shear rate and the signature for polymers. So if it's a Newtonian fluid, it doesn't matter. Like for the oil, it's just a constant viscosity. No matter how fast you spin it, the force is going to be proportional to the speed you spin it. Right? The faster you spin it, the more the force, and they're 1-to-1. Nothing changes. Right? That means it's a constant viscosity. And then in shear thickening fluids, like an egg, when you whip up an egg, this thing's going to increase. And then in shear thinning fluids, it's going to decrease. Usually that would be like a power law fluid. So you have like a log of these, then you're going to see a power law decay. But if you go to a slow enough point, again, like the chains are stretching out and they don't have time to relax down to that random walk. So there's some point where there's some time, 1/tau equals this gamma dot, where they have time to relax and then they become a Newtonian fluid. Right, so that's called the Newtonian plateau. I guess we call that Newtonian plateau, and usually it's even 0 knot or whatever we call it. So that's how you get that number. And the signature of a polymer is that shape. That means you have a polymer. That's more or less like you could say that's a photograph of a polymer for a rheometer. You know, so if you see that shape, you know that you must have something like that, and it must like straighten out here, and it must coil back up here. In terms of the time, like the 1/time that you're looking at space here. So you're going really fast, going really, let's see, 1/time is a space here, that's true. And that's relaxation time. This should be long times for short, long times for short standard. Anyway, so that's the idea. So you're going really fast over here, can't relax and things straighten out. You're measuring the force on a straightened out thing. Anyway, so that's what the answer, it's kind of a long answer, but that would be the answer to this question, which 2 groups got. I guess I gave you 5 points if you said that, 5 extra. If you said something kind of coherent about that. And then, so then, you can see, like I said, there's no connection between rheology and morphology, but every explanation for rheology is going to be morphology. It's kind of like you're lying all the time when you're talking about rheology, more or less, right? So you can't help it because it's too complicated otherwise, right? So anyway, so that's polymers. That's basically polymers. That tells you it's worm-like micelles because there's no polymer in the system, so it has to be worm-like micelles. You know? And then the other ones on that back up here, like this one is weird. So you could say, I think everyone kind of said something about that. These 2 are like elliptical and maybe just spherical micelles, and they transition into worm-like. Then the weird thing is that it doesn't change with concentration and with mixture ratio at some point. So they're all like pile on top of each other at some point. So that's pretty strange. So you have to say like the answer to that is that the structure doesn't change. Like it's the same structure, meaning the length of the chains is the same, whatever branching is the same, everything's the same at some point, right? So it's kind of anyway, so there isn't really an answer to, I mean, you could think about why, but basically the answer, when they're the same here, it means they have the same structure. even though I said rheology doesn't have to do with structure, but basically the only way you can interpret it is the structure doesn't change there. Or two structural changes compensate each other, like the chains get longer, but they get branched. So when they get branched, the viscosity drops because the branches are mobile somehow. That's a theory of this guy Cates, this other paper in here somewhere. That, I mean, so anyway, whatever that's worth, that was the answer to that thing. And 5B shows that then this 5B, I wanted you to go back to, oh, I don't have that open. Huh? Let's see. I have this guy open. There's a picture in here. Oh, okay. So in here, there's a picture somewhere. In slide 7. No. Right here. So this little thing here from Fried's book. Fried was a professor here, right? So anyway, the book's on the webpage too. It's kind of a pretty good book. But you can't really read the lines in this thing. It's unfortunate, but here. All right, so this is called N eta SP, right? Not eta naught. So we have eta naught, this is eta SP. So eta SP is something different, a little bit different. So anyway, what eta SP is, if you look at our paper, so our guy, so you see like this falls apart over here. So if you think about it, so the solvent here is water. Water's viscosity is 0.001, like if it's 20 degrees C and it's pure water. And salt water is a little bit higher. So basically, this is like landing at water, and you could dilute it down to just be the same plateau viscosity because you get the plateau viscosity of water. So that means that looking at this curve here is kind of useless because it's just going to be water's viscosity, no information. So what you want to do is take this viscosity and subtract off water. That gives you what's called the relative viscosity. And it's in same units of viscosity. It's just like the difference between the solvent and the thing. And then if you want to go even further, you would divide by the solvent viscosity and you get the specific viscosity, which gives you a number. Where's that thing? Here, like this. Okay, so once the relative viscosity would have this power law 1 and a log. The specific also has a power 1 because it's just changed by constant, which would be a prefactor, like shifting this up and down. So the reason why one reason why you go to specific is because at this 1 times 10 to the 0, which is 1, that means that the additional viscosity from the stuff you put in matches the solvent viscosity. So you have double the solvent viscosity when this thing has 1. And somehow, when that thing is 1, is like an empirical place where entanglements begin. That's the viscosity where you can say, oh, it's going 1 because you just add more stuff. Every time you add stuff, you get the higher viscosity proportional to how much stuff you add, which you would expect. Then at some point, all hell breaks loose and just shoots up because entanglement, new mechanism, entanglements show up and the thing becomes really viscous on a log scale. So it's going up like 5 orders, right? So anyway, so this one reason to get specific is so you can get this 1, and 1's a magic number. Here it's like a little bit above 1, significantly above 1, I guess. But basically, that should be the magic number we expect to see entanglements. So you can do that with our thing too. Did it here somewhere. I stuffed in. So I link a new tab. Let's see, where did that go? That's pretty weird. Open link a new tab. Right, just open link. We're gonna do that way. Let's see. Where's my thing? Viscosity. Maybe this thing's a dead link. Oh no, it downloaded it. Okay, over that. All right. So I digitized their data. That's the red curve. And I subtracted off, so I got the relative viscosity, where it says viscosity. The second one's relative. Subtracted off the solvent. 0.0011 I took off. And there's kind of a region of power 1. That's just add in more, you get more. And then I divide it by water and you get this curve, which is kind of the same. So it doesn't change it significantly, except it kind of shows the power one is there. And then this thing also just blows up. But an advantage is you can go to one and you can say, well, that's where entanglement should show up, and they kind of show up there. So you could say like entanglements are showing up here. And that's where this thing shoots apart. And then all kinds of things happen structurally, I guess, is why it's doing this. I think a couple people gave pretty elaborate, good answers to why this thing shot up. The paper talks about it. I mean, it should, it's just a linear polymer. It should look like that. Like it should just go like power 3 over here and power 1 there. So anyway, that's that question. That business. Then 6, like some of you could see and some couldn't see. So it looks different than the random walk. You know, so it looks different because it's got you have to really blow the thing up to see the endpoints and things. So I mean, it's stretched out here because of the processing, and it's more random walk around the edges. And then if you look, you can see end groups and stuff. So like that's a branch point because it isn't darker in the middle. So if 2 of them overlap, it's darker. That's an entanglement. If it's light, if it's the same brightness, it's a branch. So I guess that's a branch. I mean, it's qualitative, right? And it's somewhere in here is an end group. I've never seen it, but anyway. So some of you have said I found the end groups, I found the branches. I guess that was good enough. And some of you said where they were, and some people said there weren't any. If you glance at it, it looks like there aren't any. So I wanted you to kind of look in and see like this. So this is the problem of like polymers, is you're looking at a gooey mess of like wormy stuff all on top of each other, and you can say anything you want about it. But basically, and these might not even be micelles. Like you're just assuming it isn't an artifact of freezing the thing in liquid ethane, right? When you think about what they take a meniscus, it's already like sub-micron pores in this carbon grid, or maybe micron-sized pores. You can't see it. You make a meniscus, you assume it's there. You freeze it in liquid ethane, which is really cold. Then you keep it at liquid ethane temperatures and stick it into an electron beam, which is known to burn things. And then you take a picture of it. The picture there, like in other words, when you take this kind of picture, you like move it into the beam, pop, and then the thing disappears because it burns it. So you're actually watching a burning process, you know. So it looks like a nice micrograph when you look at it. It's very difficult to get these. And then anyway, so basically you can, to say too much about this is probably not a good idea. That's the point, but all right. So anyway, that's that. I think that's the whole thing here. Any questions on this? Seemed like the answers were pretty good. I mean, especially at first pop, but at homework.
Is there evidence on like the end of the chains on that you can see visually?
I could see it. I mean, I saw it before. Yes, there is. There absolutely is in here. I've seen them in here, but right now, you'd have to follow through. Like, now that's hard to tell. This one, I think you can see end groups. And so someone pointed out here, there's one, maybe there's one there. There might, no, that's a branch, right? Or so I think there's end groups in here. I saw one once. I don't see it now, but yeah. Yeah, there are end groups in here. Here, is that one? That could be one right there, maybe. It's pretty hard. It's like I said, like there's probably one right there, I guess.
Honestly, I could only just kind of like guess. Like I think this is one. Like...
Yeah, you're right. Right now, I don't exactly see one this definitively, and right here, how about that? That's kind of could be a. It's dark though, so that's on top of the one below. So that's an end group. That one, that little thing right there, and this one below it might be too, but it's a little bit hard to tell. But that one definitely goes on, and then it's dark because you have 2 of them, one on top of the other, and that one's an end. And that's just a chain. According to my careful scientific definition of what's going on here. So I see an end group. I see at least one, you know, meaning that, right, so from that you could calculate how long these chains are, I think. Like, so I think if you figured out how many chains are here, and then how many end groups are here, So if you count all the chains here and you find two N groups, so you have to find more than two or more. But if you find two N groups and count all the chains here, then that's all those chains, that would be the length of the chain. Right? Statistically, you'd get the length of the chain. If you find four N groups, count up all the chains here, divide by two, that's the length of the chain. So if you can count the N groups, you can get the length of the chains. Right. So yeah, in polymers, like the big thing is going to be like getting the molecular weight because they're such. Do you have a question?
Yeah,
Huh?
are there any similarities between this and DNA?
Yeah, is there similarities between it? Yeah, like a lot of times because DNA is so big, it's easy to see. It's like I'll show you pictures later on of like some of the dynamics of polymers, and people use DNA to look at it to show like how polymers behave when they move, you know. So it's so big you can see it in like a SEM or even like a, I don't know, some kinds of optical microscopes you can see. So you can watch the dynamics of the chains, and then they say like that's the same as some, I guess, theoretical predictions for polymers, and then this kind of complex connections between there's ways to measure the structure of scattering, but then it isn't like a photograph, you know. The DNA, you can get a photograph. So the difference is DNA, when it gets large, like, so it's talking about things that are subject to like KT, like diffusive motion, like molecules. And so polymers are subject to diffusive motion. And when you get to the size like microns, diffusive motion like KT isn't really at play as much. It's more like gravity and inertia and things matter more. So the connection between macroscopic and like atomic level is a little bit loose, and the biological things are kind of in between, you know. So at some point you have to say, well, gravity is going to affect this thing. So you have to kind of consider that. But yeah, a lot of people use DNA as a model. These are smaller than DNA though. So these are what, 40 nanometer diameter, I think. So I think they're smaller. Anyway. So anything else on this thing? I can kind of give up on that. So, oh, there's one more thing. So he's got, which I wanted to go through today, but anyway, he's got this thing. So I didn't mention like what that is. So what that is another way to talk about polymers, you know, another definition of polymers. You have this same rig. So you have this rig. Right? So if you take that, so one way to run this thing is to just spin it, right? Another way to run it is a low amplitude oscillatory shear, something. I think it's one more letter, but basically instead of doing that, you're going to spin it. You're going to oscillate it with an acoustic frequency. So you're going to go. So you like the curve for viscosity is like 10 to the minus 3 or something, 10 to the minus 2, 10 to the minus 3. So that's like acoustic sound waves, like high pitch, like kind of thing, right? So and then you can go, and then the high end was like 1 hertz is kind of in the middle, and it's like 10 hertz. So it's like that. So when you run these things, it's going to make a noise like this kind of like digital sound noise, right? And you're going to do this, and the amplitude of the oscillation is going to be like less than 1% oscillation of the thing, right? So basically, it's going to vibrate back and forth. So you have the strain. The strain's going on the sine wave. Right? So it's going like that. And then the stress, the torque that you get out of it isn't in phase with that because of viscoelastic. So if it was a Newtonian fluid, then the stress response would be like that. If it was a solid, the stress response would be like 90 degrees out of phase from that. So I guess like that or something, or it would be destructive, right? So, but somehow the thing would be like that. Or it was a solid liquid. So solid is like 90 degrees out of phase, and then the liquid is 0 degrees out of phase. And the viscoelastic is halfway in between. So you can think about this like, so you think the liquid is like a loss kind of thing, and the solid is like an elastic, like a Hookean elastic response, right? So anyway, so basically, if you take a rubber ball, it's kind of a good thing to look at, and then it hits the floor and then it bounces back up some, right? So this amount is like the loss, and this amount is the elastic. Right, so you can say like if the ball deforms, so you have like the stress on the ball and the strain on the ball, there's a modulus in between. Right, so this modulus is going to have two parts. It's going to have like the loss modulus and elastic modulus. So here, because we're doing shear, they would call it Young's modulus. They call it the shear modulus G, and then it's the strain and the stress. Right. So anyway, so you'll talk about this kind of measurement as in terms of this G being a complex number. It's got a real part, which would be like the storage, and then kind of a imaginary part. This is the loss part. So you have this G prime, G double prime. And if you plot, so those things are functions of this rate, like the rate that you're deforming it. So if you think about, like you can throw a rubber ball against the wall hard enough, it can shatter like glass, right? Or you can throw it slow enough and it'll bounce. And if it's not cross-linked, it'll flow at some point. So if you take long times, so low strain rate, then basically you can get a liquid behavior. So it's going to have a transition. It'll have a rubbery behavior in the middle. Then it's going to have like elastic behavior at the high end. So you expect to see what's called a crossover in these plots. You're going to have G prime, G double prime plotted against the strain rate. And then you're going to have G double prime higher at the low strain rate and G prime higher, lower at the high strain rate. So that's a liquid. Then there's a crossover frequency here, which is the point where the storage and loss are equal to each other, and then the G prime will go up and plateau out. That's a rubbery plateau on the thing, and this other things happen here. So basically, people talk about this crossover frequency. So whenever you're looking at these plots, you're looking for there's going to be some mess like this, a solid thing. The storage modulus black blocks, which are solid, is storage, and hollow or the G double prime the loss. So when they cross, that's a crossover frequency where it's going to turn into kind of a solid when you go to higher frequency. In other words, if you throw the rubber ball into the wall really fast, it'll smash. So same with a person when you jump off a bridge. There's something about water has this behavior too. I guess water at high speeds is like concrete, apparently. So don't jump off a bridge. Doesn't sound good. Anyway, so these guys are going to cross. So you have the hollow circles, and then the dark circles of the. So here it's a liquid because the hollow are above the solid. Then the oh shoot, sorry, yeah, sorry about that. All right, so all right, to me it made perfect sense. So right, so the hollow, that's the loss, and the solid ones are the solid are the elastic, and the hollow are the lost ones. So at low frequency, it's liquid, and then it crossover frequency here, and that becomes a solid. All right, so that's kind of a preliminary part to this picture of these things. So if you want to look, so this is some frequencies. So you can get, see if you measure this one temperature, you can get a set of frequencies like this. If you want to get more in a polymer, then you do it at different temperatures, because also getting it colder makes it more solid. So the time temperature superposition, like an Arrhenius function that relates time and temperature. So then you can measure different temperatures and then expand this range. You can get many, many decades, right? And then you can look at the entire polymer picture in terms of like what the structure. So again, it's viscosity measurement being described in terms of a modulus. So the loss modulus divided by frequency is a viscosity. Yeah.
Well, there's a crossover point.
This is a crossover here. Yeah.
That's like a change in how you
That's
categorize the phase type.
No, that's a change in the behavior of the material. The phase is always the same. So this isn't thermodynamics. This is like dynamics. So the thing is how it behaves. So it's going to behave if I wing a rubber against the wall, it's going to act like glass. And if I put it on the table and it's not cross-linked, it'll flow. It'll make a puddle, like silly putty. Right. So if you can shoot silly putty out of a gun, it'll break like glass. If you leave it on the table, it flows. Right. So long time, short time experiments.
It's the same phase, but how it responds to stress.
It's the same phase. It's just it's got to do with the structure, like the time of how the chains can move. Right. In other words, if it has enough time to move, it'll be a liquid. So it can escape all those entanglements and just make a puddle. right? But if it doesn't have time to move, it's stuck, it's a glass, and then it'll just break. So it's a matter of the time that it can, the time that for the relaxation of the chains.
What's the use in knowing that point? Look like that. And then-
I mean, that's like the glass transition at that kind of, it's like looking at the glass transition temperature for the material at that frequency, you know, so basically kind of 1 hertz is where we live. So if that thing is below that, it's a glass. If that thing's above that, it's a liquid. So if you wait long enough, I mean, they used to say that the windows in the cathedrals were thicker at the bottom than at the top, which apparently is a lie. Apparently that isn't true, but yeah, so they've debated that over a number of years, but I think the consensus now is that they aren't thick. They're thicker at the bottom, kind of because how they were made, not because of the flow. But there is a place in Australia where they're looking at flow of what's the stuff in pine trees to make kind of, so not the sap, the rock thing. No, that begins with A. It's like a rock. Amber, yes. Somewhere in Australia, they have a video camera on a piece of amber that's been flowing for like 100 years or something. And like they're measuring the viscosity of that amber. It's kind of a famous thing in rheology. Anyway, it's on Wikipedia somewhere. You can Google it. You can get a video of it. But anyway, so yeah, if you wait long enough, it's a liquid. So that's a viscoelastic, same kind of thing. So it's, yeah, so you're saying like, it's not a phase change, it's just the stuff behaves differently. Yeah.
So would it be wrong to say it behaves like a ceramic? Like, does it have like full ceramic properties, or is it?
No, there's no
general-
crystals, it's a glass, it's just stuck. So it's like if you have like those coffee bags when you get ground coffee and it's vacuum packed and it's like a brick. Has anyone ever seen this? You vacuum pack it, it's like a brick, and you can hammer a nail with it. If you cut it open and like a little bit of air gets in, then it's just like a pillow, right? So it's the same kind of thing. It's not a crystal at one end and not a crystal at the other. The things are just stuck, like they can't move. Because they can't move, it's a solid. So that's kind of what's going on here. The things are stuck because if they have enough time, they'll move, but they don't have enough time. So that, yeah.
I thought it was the pitch from the pyramid.
Yeah, that's it. All right. That's not amber. Okay. Okay. Yeah, I remember looking at the video, but I don't know. Yeah. All right. Thank you.
Going on for 50 years.
Yeah, it's like and you can there's a web page where you can actually watch it continue doing
No one's
nothing.
ever actually seen it, but apparently it's stuff like
Oh, really? All right. Oh, you mean it drops of it come off or something?
yeah, but like
All
no
right.
one's ever actually been able to see it. And no one's
All right.
seen it fall.
Okay. All right, well, there you go. That's why rheology is so exciting in the field, you know, it's like, anyway, so that's the kind of idea here is that, I mean, time scale, we look at it, it's a solid. On the time scale of like dinosaurs or something, it isn't, right? So it's totally a liquid, right? So this is measuring different time scales. So you can see these kind of transitions. And also there's something to do with the frequency and the size. Like if you have a big bell, it's a low frequency. If you have a small bell, it's a high frequency. Right? That's got to be generally true. Like all the times you hear little bells, like little teeny things, and they're high pitched. Right. So basically you can say using the bell theory, you know, that you have basically you're looking at big things over here and small things over here. So how big and how small? Like on this end, you're talking about literally an angstrom. Right, at this high end of frequency. And at this end, you're basically looking at like meters. So it's a huge range. So it's like, that's something like 6 or 7 orders of size. And this one machine that just goes, you know, it's like a simple lab machine. You can probe sizes from an angstrom to a meter, which is, that's kind of interesting if you think about it. On the other hand, you can't really probe sizes at all because it isn't really connected to morphology directly. Like everything is linked in a complex way, but still. So anyway, so because of that, people have spent a lot of time looking at the details of this. So there's one crossover here, and at really high frequency is another crossover. And this has to do with the structure of the polymers. Kind of like this is a relaxation of the chains, the entanglement tube part. Then this is within you say the chains are weaseling through kind of a tube of other spaghettis and the size of that tube. So within a tube, they can move like a normal flow, like flow like a fluid within the tube. So when you get to really small sizes, there's another crossover and becomes a liquid again, like on a on an angstrom scale of the chain, the diameter of the chain. So this is kind of like the chain diameter almost. Then all of a sudden you have flow again. So you have flow down here, flow up here. There's symmetry between the two. In between, you have a rubber plateau. The modulus becomes constant because that has to do with the distance between entanglements, not the, I'll talk about this more later on, but basically of things to talk about, like how polymers, how you describe polymers, that's one of them, right? So we have like, let me shrink this down somehow. So we have like the chemists looking at this thing like that. Then we have kind of the rheologists looking at features of flow. And then this kind of, we have the crystallography looking at the thickness of the crystals, plateau out. And then this business of the entanglement showing up. And then finally it gets to be like a picture like that, which is, so all the rheology people are going to show everything in terms of this modulus, even though they're measuring rheology. Because it's kind of it's easier to understand the structure of the thing rather than the times of it. I mean, the viscosity is a little bit harder to put your hand on. And then there's scattering is kind of like the other part of this thing. So scattering looks like this. So you have like a log scale here, and so this is inverse time, scattering is inverse size. And you have something else plotted here. It's like kind of like the amount of the stuff. So this scale, so this is a signature of a polymer scattering. So you have power laws here. So log, and this power law is power 2, power 1. So what is going on here? So you have this Q thing here. So if you're coming in with a beam, so the experiment here is like this. It's just like diffraction. So you have a beam coming in. If it's X-rays, it's 1.54 angstrom for a copper target. And you have your stuff. And then it goes out. So this is really bright, like maybe 10,000 times brighter than whatever comes off here. So that's the scattering comes off of it. So if you think about it, so this thing is a wave like that. You can just say that wave is just like a bunch of lines. And then if you have some structure in here, this is elastic scattering. So the wave coming out here is the same wavelength as that one. So it's also a bunch of lines. So the point here where you could create a wave. So this wave comes in, excites the material, so excites the electrons in the material. There's an oscillating wave, and they give off the same radiation. They re-radiate it and kind of isotropically, right? So the places in here where that could happen is where the stuff is, like whatever the thing is. So if you think about that, you have so you have the incoming beam is this the horizontal kind of grid of stuff. Then the outgoing beam is this one. And the places where these lines coincide with those lines are these fringe patterns. So that's what this Q is. Q is going to be kind of 1 over that spacing, right? So when you go to small sizes, that thing, oops, you want to do that. Let's see, undo. There. Wanted to do this. So you go to small sizes, that spacing gets big. And when you go to large sizes, it gets small, and it reaches like 1/2 of the wavelength at some point, right? So you have kind of 1/2 the wavelength is the smallest thing you can measure. And the biggest thing you can measure at small angles is like infinity. So you measure, it's a space where you can see very large things up to infinity, but you can't see small things. You're limited at the wavelength for the thing. So if you think about small angle, big angle, small, that's kind of the way this picture is. Like this is inverse size. And this is an angstrom, and that's about a micron over here. And this is using neutrons, not X-rays, because neutrons have the deuteration thing. You can deuterate the chains. And then, so this thing's kind of like the mass. So if you have, so intensity is proportional to the mass. So if you say you have the mass on one side and you have 1 over size on the other side, if you have mass and size, then that's going to go, like if it's 2-dimensional, that's a plate. If it's 1-dimensional, that's a rod, right? And then, so this is the dimension of df. And this random walk thing is a dimension 2. So you expect to see in this plot, So it's not +2, it's -2 because it's 1 over size. If you plot log intensity of say mass versus log of 1 over size, you expect to see 2 here for that random walk thing we did. And then you expect it to end some point at the size of the coil. So that's the coil size. Then you expect to see something down here where this thing starts to look like a rod. So it'll go to -1 there, and that's the length of the rod, or the persistence length, or the Kuhn length. I just expect to see that kind of behavior on this thing. And that's kind of what you see here. Right, so you have, this is polyhydroxybutyrate, so it's a biodegradable plastic. You make spoons from it. And then it's in deuterated solvent, deuterated THF. And then basically this is the coil size. That's this dimensional part where it's acting as if it's a random walk, just like the random walk we did with diffusion. It's a dimension 2. And there's a little bit of this step thing here, like power 1. So you have 2 sizes that come out of this: the coil size, the step size, and you have this dimensionality of what the chain is. So this is a chain, one chain in a melt, like a deuterated chain in a melt, actually. Right? So it's not in deuterated THF. This is a chain in a melt, deuterated polyhydroxybutyrate and hydrogenous. And then, so there's other things you can get from this. Like here, you can get the composition, because intensity of the scattering has to do with what the stuff is. And then that's it, I guess. You can get the dimensionality, the sizes, and the composition. And that. So that's another way to look at. So someone saw this scattering curve, they say that's a polymer. Just like if they looked at that curve, they'd say that's a polymer. Just like if they looked at this curve, they'd say that's a polymer. Right. So these things are all look kind of different than the chemist or the crystallography people or the chemist kind of view of what a polymer is. Right. So anyway, that's about what we have time for today. So I'll put together another homework and something, and some of this stuff. You know, probably.
All public do Tuesday as well.
Yeah. I didn't change that yet. I'm not
Afternoon.
afternoon. Yeah. If you're having a hard time, all right, email me, like if you totally like can't figure out what's going on, I'll give you some hints, and then
I totally know Jesus. Do you want some context? I mean, like,